Okay, sir. Okay, sir. Yes, sir. Okay, sir. Yes, sir. Yeah, good evening, friends. So I'm starting set one. So the first question I'm displaying this one, like the heat transfer question. Yeah, that is regarding the healer charts. Okay, a hot steel spherical ball is suddenly dipped into a low temperature oil bath. Which of the following dimensionless parameters are required to determine the instantaneous center temperature of the ball using healer charts? Okay, in healer charts, we know that healer charts are used for what kind of this one healer charts? Healer charts are used for transient heat condition. Okay, in healer charts. So for center line temperature, so on y-axis we'll have T naught minus Ti, T naught minus T infinity by Ti minus T infinity. On the x-axis we'll have Fourier number. Sorry, a Froude number. That is Fourier number, that is alpha. Sorry, Fourier number, that is alpha T by R naught square. So okay, and so we'll be having plots like this. Okay, so this indicates your value of k by h r naught. Okay, so this Fourier number f naught, okay, so is on y-axis, is an x-axis. Okay, and the variable is k by h or not. Okay, so what is the k by h or not? We know that what is Biot number. Biot number is equal to HLC by k, so that is h into v by a by k, so that is equal to h into what is the volume of this sphere, that is 4 by 3 pi r cube by what is the surface area, 4 pi r square. Okay, here we will be calling it as r naught. So then this will be h r naught by 3k. Okay, and here k by h r naught. Okay, what is this? Is Biot number. Okay, 1 by Biot number is nothing but k by 3k by h or not. Okay, so which is nothing but 1 by Biot number is proportional to k by h or not. Okay, so the independent the dimensionless parameters required for central line temperature are Fourier number and Biot number. So that is Fourier number and Biot number is the answer. Biot number and Fourier number is the answer. Okay, so then we will go for the next question. Okay, so that is the seventh question. Yeah, this question we can discuss. The fifth question also we can discuss. That is a cantilever beam is given. So there is a load at the end. Okay, so they are asking for the deflection at the center. So the deflection at the x is equal to L by 2. So from here, so x is starting from here, and this is the total length L. So they are asking about the deflection at the L by 2. Okay, so for this we can use moment area method. So what is the bending moment diagram for this? So bending moment diagram will be like this. So this is M and this is also M. Okay, this is minus. Okay. Okay, so now so and M by EI diagram. If I plot M by EI diagram, it will be a rectangle only. Okay, and so we want to have the deflection at the center. So for that, actually, what you have to do? Okay, so now so and M by EI diagram. If I plot M by EI diagram, it will be a rectangle only. Okay, so you want deflection at the center. So we have to take the moment of M by EI diagram, about the midpoint. So this one. So deflection at x is equal to L by 2. Deflection at x is equal to L by 2 is nothing but moment of moment of M by EI diagram, moment of M by EI diagram about x is equal to L by 2. So that is at midpoint, this point. Okay, so this is, let us say, A, B, and this is C. Okay, so what is the area of this one? What is the area of this one is M by EI into L by 2, and moment is from here to here. So how much is the distance? This is L by 4. So L by 4. So this is your deflection. So that is nothing but delta is equal to ml square by 8EI. So this is the answer for deflection. Okay, so now let us go to the next question. So this is another question in fluid mechanics. Okay, so here if you see a cylindrical jet of 1000 kg per meter cubed impinges on the center of a flat circular plate and spreads radially outward as shown in the figure. The plate is resting on a spring of constant k is equal to 1 kilonewton per meter. Okay, the incoming jet diameter is d is equal to 1 centimeter. So he is asking the deflection of 1 centimeter is absorbed in of the spring. So 1 centimeter deflection is observed. Then he is asking what is the velocity? What is the velocity of this jet here? They are asking. Okay. Yes, sir. Yes, sir. Yeah, seventh question we are solving it. Okay, so that is impact of jets problem. It is very simple question. It is one jet is impinging onto the circular plate. Okay, whose diameter of the jet is 1 centimeter. Okay, and it is impinging on a circular plate. The circular plate is supported on a spring whose stiffness is equal to 1 kilonewton per meter. So that is equal to 1000 Newton per meter. Okay, so it is impinging on this some velocity. Let v be the velocity of jet. Okay, so it is impinging on this one. Okay, on the circular plate. Okay, so what is the force exerted? What is the force exerted by this jet onto the circular plate? Force exerted by jet onto the circular plate. F is equal to, so rho a v square. Okay, so what is rho? Rho is density of the liquid, that is 1000 kg per meter cube, and a is nothing but cross sectional area of jet. So that is equal to a is equal to pi by 4 d square. So that is pi by 4 into, so 1 by 100 square. So this is around 7.85 into 10 power minus 5. Okay, so then what is the force exerted? This will be F is equal to rho a v square, and so because of this force only, the spring has been deflected. So what is the deflection of the spring? Okay, so how will you find out what is the deflection? Deflection he has given as 1 centimeter, that is equal to 1 by 100, that is 0.01 meters. Okay, so that is k is equal to, what is the definition of k? K is equal to force by delta. So then, okay, then substitute the value of k. K is nothing but 1000. 1000 is equal to F is rho a v square, that is 1000 into 7.85 into 10 power minus 5 into v square by delta is 0.01. So then v will be around, you will be getting the value of v is equal to 11.29 meter per second. So you can, if you have any doubts, you can ask me in the chat. And please subscribe to this channel. So this is the answer of this velocity of the jet. So let us move on to the next question, that is from vibrations. Okay, so that is the next question, that is from vibrations. Okay, sure, sir. Yeah, sir, yes, sir. Yeah, the next question is on vibrations. Okay, the vibration problem is asked is little bit difficult, but if you so this is a hinge having at B. So this is A. So this is B. So here there is a push start. Cam. Okay, so this is cylinder head and this is a spring. Okay, this is a valve. Okay, but they told that the mass of push rod and your valve is negligible. Valve is negligible. Okay, but the push rod is having a stiffness. So stiffness of push rod is stiffness of push rod is K suffix P is equal to 15 Newton per mm. Okay, that is 15,000 Newton per meter. Okay, and similarly, stiffness of wall, that is kV, that is equal to 10 Newton per mm, that is equal to 10,000 Newton per meter. Okay, so this problem is like a horizontal lever problem only. So in vibrations, you studied this kind of problems. Okay, so it is like a horizontal lever, okay, which is hinged at one point over here. So this is A, and this is B of push rod. This is Kp is equal to 15,000 Newton meter, and this is Kv is equal to 10,000 Newton per meter. Okay, and this is A is given as 3.5 centimeters, and B is given as 2.5 centimeters. So A is equal to 3.5 centimeters is nothing but so B is equal to 2.5 centimeter, nothing but 2.5 by 100. So that is 0.025 meters. Okay, so this is a hinge point B. Okay, now we have to take the moments about and give a small displacement to the lever. Either in clockwise or so this I am giving anti-clockwise moment to the lever about this hinge point. So now this is your A and this is your B. We will rough these things. Okay, after giving displacement, this is your A and this is your B. And what about this value? This value will be is A cos theta. And similarly, this is B and this will be equal to B cos theta. And this will be B sin theta. Force will be downwards. So FSP is the spring force of push rod, that is equal to Kp into A sin theta. Okay, and this is being compressed, so your spring force will be upwards. So this is your FSV. Spring force of valve. So that is equal to kV into B sin theta. Okay. Now this has been rotated by clockwise. So your inertia torque will be anti-clockwise. So that is Ti. Okay. Ti is nothing but Ib into theta double dot. That is equal to Ib is nothing but Ib. They have given already value. Okay. So let us keep it as like this. Now take the moments about all the forces about B is equal to 0. So now Ti is anti-clockwise plus FSB into B cos theta. So this is also anti-clockwise plus FSB into A cos theta. A cos theta. Okay. So Ti plus FSB is this value, that is Kf into B sin theta into B cos theta plus FSB is Kp into A sin theta into A cos theta is equal to 0. Okay. So now for small angles, we can say sin theta is equal to theta and cos theta is equal to 1. Then this will be Ib theta double dot plus Kv B square theta plus Kp A square theta is equal to 0. Okay. So Ib is nothing but, okay, let us substitute these values into this. Okay. So now let us substitute the values. So this is 10 power minus 4 theta double dot plus 10,000 into 0.025 square plus 15,000 into 0.035 square into theta plus 24. So that will be, so it is looking like mx double dot plus kx is equal to 0. So what is the omega n? That is root of k by m. So that is nothing but 24.625 by 10 power minus 4. So that is equal to radian per second 60. So that is equal to 496.23. Then n is equal to 4738.65. So it is around 4739 RPM. Okay. So this is the answer. 4739 is the answer. Okay. Now we'll discuss one more question in the vibration problem only. So they have given like this. So at particular time, so this is the displacement versus time. Okay. So this is at time t1, the displacement, the maximum displacement is or amplitude is x1, and after one cycle, the amplitude is x2. After one more cycle, so the amplitude is x3. After another cycle, the amplitude is let us say x4. Okay, this is first cycle, this is second cycle, this is third cycle. Okay, so they have given the value of displacement at particular time and after three cycles. After three cycles, that is nothing but x4, that is equal to 1.5 mm. Okay, so we know that x1 by x4 is equal to x1 by x2 into x2 by x3 into x3 by x4 into x4 by x. Okay, oh sorry, x3 by x4 and up to. So this we don't have to write it. Okay, so then so x1 by x4, that is equal to x1 by x2 whole power 3. Okay, since we know that ratio of successive amplitudes is constant, that is x1 by x2, that is equal to x2 by x3, that is equal to x3 by x4. Okay, then x1 by x2 is equal to x1 by x4 whole power 1 by 3. Okay, that is equal to x1 is how much? 8 by 1.5 whole power 1 by 3. Okay, so then apply log on both sides. Then this will be ln of x1 by x2 is equal to ln of 8 by 1.5 whole power 1 by 3. So that is equal to 1 by 3 ln of 8 by 1.5. So that is around 0.56. Okay, and zeta. So we know that they are asking about zeta, damping factor zeta. Is equal to question mark. So here we know that logarithmic, this is nothing but logarithmic decrement. So once, what is the formula for logarithmic decrement? Logarithmic decrement delta is equal to 2 pi zeta by root of 1 minus zeta square. Okay, we know that. Okay, so from this we can write zeta is equal to delta by root of delta square plus 4 pi square. So that is delta is how much? 0.56 by root of 0.56 square plus 4 pi square. So then zeta will be around 0.089. So this is the answer for zeta. Okay, now we'll do one more problem. That is the 15th question. So they are using two sheets of two plates, two thin sheets or sheets. Okay, and so each is around 1.5 mm thickness, and they are welding. They are joining these two plates by using friction. Sorry, that is resistance spot welding. Okay, so and we are able to get a weld nugget over here. So this is your weld nugget. Okay, so there, yeah, the values they have given as welding current, that is I is equal to 10,000 amps, and so time taken for welding, that is T is equal to 0.25 seconds. Okay, contact resistance of, that is capital R, is equal to 0.0001 ohms. Okay, and they are giving, so we can calculate heat these things, that is I square R, that is I square R into T. So that will give the value of heat supplied in joules, that is 10,000 square into 0.001 into 0.25. We will get the value of heat in 500 joules. We'll be getting okay. So and heat required, yeah, heat required for uh, unit volume is equal to, heat required per unit volume is equal to, they have given as 12 joules per mm cube. So the total heat required, let us say QR, that is nothing but 12 into 70. So that is around 840 joules. Okay. And they are asking for what is thermal efficiency. Thermal efficiency of welding process, that is equal to heat required by heat supplied, that is 840 by 2500, that is nothing but 33.6%. So this is the answer. So what is the welding efficiency, thermal efficiency they have asked? So that is around 33.6. So that is another question. So let us now start with some other question. So let us solve with one more problem, that is a thermal science question. So it is related to a question of compressibility. This is a compressibility factor related question. Okay, so they have given the specific volume of steam. Specific volume of steam as, okay, V bar, let us, that is 2.75 meter cube by kilomoles. Okay, and they have given compressibility factor. Compressibility factor as Z is equal to 0.95, and they have given the pressure of superheated steam as 1500 kilopascals, and they are asking what is the temperature of this steam. Okay, so we know that compressibility factor Z is equal to, what is the formula for compressibility factor? PV bar by R bar T. So that is nothing but 0.95 is equal to P is 1500 into 10 power 3 into 2.75 by R is, what is the value of R bar? R bar is nothing but 8.3143 into 10 power 3. So R bar is universal gas constant, that is 8.3143 into 10 power 3 joule for kg or kilomole K. Okay, so then this will be around, yeah, that is 8.3143 into 10 power 3 into T. Okay, so that from this we can get the value of T in kelvins. So we'll be getting the value of T. So is around 522.24 Kelvin. So that is equal to, we have to convert in degrees because they are asked in degrees. So then this will be, so 522.24 minus 273. So this will be around 249.24 degrees centigrade. Okay, so the answer is 249.24 degrees centigrade. Okay, so now let us go to the another question. Okay, this I'll just introduce the slides. Okay, so now we'll solve one more question in machine design. That is 24 question. This is an unexpected question in the welded joints. But the last 2-3 years they have not asked in question in welded joints. But they were asking only the question in till now they are asking question in parallel joint or transverse in parallel lap joint or transverse lap joint only they were asking. But this time they have asked somewhat in the means a time taking question. It's not difficult question, but it will take time, and so just we need to understand. So what are the stresses that are generated in the weld? So this is 40 mm. This is 50 mm. Okay. So we need to find out the what are the stresses that are generated in the weld first. So for that we have to transfer the load to weld. Okay. So after transferring it, so what are the things will be there in the weld? So let us say this is P and this is E. Okay. So if I want to transfer it, we have to apply equal and opposite forces over here, this P and this P. So this P will create a couple, that is a bending couple, that is M is equal to P into E, and this is P. So now the weld is subjected to a load P and a bending moment M is equal to PE. Okay. So what is the effect of P first? We'll see the effect of P. So this is your throat thickness and this is your H. Let us say this is H and this is, let us say, B. Okay. So this will produce direct shear stress. that is tau. Tau is equal to P by throat area of welds. That is nothing but P by what is the area of each one? TH into TH, that is 2 TH. Okay, and T is nothing but throat thickness, that is nothing but 0.707 into S. Okay, what is S? That is nothing but S leg size. Okay, so now you tell me what is the value of tau. Tau is equal to P is 2000 by 2 into 0.707 into S. Sorry, that is 0.707 into S. Then this will be around, the value of this is around, sorry, into your 40. That is your H. Okay, so that will be around 35.36 by S Newton for mm square. Okay, so now, so we'll see the effect of M, that is equal to the bending moment. Okay, so this M, that is nothing but a bending moment, will create bending stress in the weld. So how will you calculate the bending stress? So using the equation M by I is equal to sigma B by Y, that is implies sigma B is equal to My by I. So this is your Y. Why are Y max? Because we are interested in maximum bending stress. So this is Y max. Y max is nothing but your H by 2. That is, so what is H here? Yeah, it's 40. It's 40. 40 by 2, that is 20 mm. Okay, so this is your weld. Okay, this is your XX. Okay, so and I, what is I? I is nothing but IXX because it is bending about XX axis. And what is the moment of inertia? This is T and this is H. And this is T, this is also H. So what is the moment of inertia of each weld about X axis? So that is TH cubed by 12 plus TH cubed by 12, like BT cubed by 12. So this will be 2 into TH cubed by 12. That is nothing but TH cubed by 6. Okay. So then this will be, just we need to substitute it. Okay. So this is sigma B max, nothing but M is nothing but P into E. What is P? 2000. Right. And what is E? E is nothing but 150. 150 by 150 into Y max is how much? 20 by, okay. And this is TH cubed by 6. What is that is T? T nothing but 0.707. Yes, into H cubed is 40 cube. Sorry. T into, so T is nothing but 0.707. 0.707 into S into H cubed. H is nothing but 40 cube by 6. Then this will be 0.707 S into 40 cube by 6. That is equal to, it's around 795.61 by S. Okay, Newton for mm square. Okay, now the weld is subjected to shear stress and also bending stress. So we can calculate the maximum shear stress. So maximum shear stress that is tau max is nothing but your sigma b max by 2 whole square plus tau square. So that is sigma b max will be getting around 795.61 by 2s whole square plus tau is 35.36 by s whole square. Okay, and they have given allowable shear stress of weld, that is tau allowable is nothing but they have given the value as to 60 Newton for mm square. And we know that for safe design, tau max should be less than or equal to tau allowable. That is nothing but 795.61 by 2s whole square plus 35.36 by s whole square should be less than or equal to 60. Okay, so from this we'll be getting the value of s as 6.65. So this is your required size of weld. Required size of weld S is equal to 6.65 mm. Okay, so that is about this design question, and one more design question we'll solve. So this is regarding the first chapter, the second chapter, design for fatigue loading. So that is machine design question again. So the load, the length of the beam is around 100 mm, and the load is varying from 800 newtons to 1600 newtons. The cross sectional area of this beam is 12 by this is 20. Okay, so now they are asking about the what is the factor of safety according to modified Goodman theory. According to modified Goodman theory. So we know that what is modified Goodman theory? It is a combination of yield line and Goodman's line. So modified Goodman theory is a combination of yield line and Goodman's line. What is yield line? If you take mean stress on x-axis and amplitude stress on y-axis, okay, so this is your SYT, this is your SYT, this is your SUT, and this is your SC dash. Joining SYT and SYT is nothing but your yield line. So what is yield line equation? Sigma m by SYT plus sigma a by SYT should be less than or equal to 1 by factor of safety. Okay, similarly, Goodman's line. What is Goodman's line? So this is connecting SC dash and your SUT. Okay, this is your Goodman's line. Okay, so this is nothing but sigma m by SUT plus sigma A by SC dash should be less than or equal to 1 by factor of safety. Okay, so they have given the values of SC dash, corrected endurance strength as around 200 megapascal and SYT as 500 megapascal and SUT as 600 megapascal. Okay, and we need to find out first of all the minimum load. What is the minimum load over here? Minimum load is 800 newtons and the maximum load is 1600 newtons. And what is the minimum bending moment? P minimum into 100, that is 800 into 100, that is 80,000 Newton mm. And what is the maximum bending moment? So we'll write this, yeah, like here. So what is the maximum bending moment? P maximum into 100, that is nothing but 1600 into 100, that is 1,60,000 Newton mm. This is 1,60,000 Newton mm. Okay, so we will find out first bending stress, that is minimum bending stress. So how will you find out minimum bending stress? So your M minimum bending stress is equal to M minimum into Y max by I. That is nothing but M minimum is 80,000. Y max is 20 by 2, that is 10 by, and I is 12 into 20 cubed by 12. So this is around 200 Newton for mm square. So this is your minimum stress. Sorry, it is 100. So maximum bending stress, it is nothing but M max into Y max by I, that is equal to 1,60,000 into 20 by 2 into 12 into 20 cubed by 12, that is equal to 200 Newton for mm square, which is nothing but maximum stress. Okay, so we have to calculate mean stress. What is mean stress? Maximum plus minimum by 2, that is 100 plus 200 by 2, that is 150 Newton for mm square. And amplitude stress, which is nothing but maximum minus minimum by 2, that is 200 minus 100 by 2, that is 50 Newton for mm square. Okay, so according to Soderberg's equation, sorry, yield line, sigma m by SYT plus sigma A by SYT should be less than or equal to 1 by factor of safety. So sigma m is 150 by SYT is, or is SYT 500 plus sigma A is 50 by 500 should be less than or equal to 1 by factor of safety. So factor of safety is nothing but a factor of safety will be getting is around greater than or equal to 2.5. So this is the factor of safety according to yield line. Similarly, according to Goodman's line, sigma m by SUT plus sigma A by SC dash should be less than or equal to 1 by factor of safety. So here what is sigma m? Sigma m is 150 by SUT is 600 plus sigma A is 550 by SC dash is 200, should be less than or equal to 1 by factor of safety. Then factor of safety is around greater than or equal to 2. So what is the factor of safety in beam? Existed in beam is equal to minimum of 2.5 comma 2. That is 2. 2 is the required answer for this question. Okay, so we'll solve one more question. That is 28 question. Okay, we'll discuss one thermal science question. Okay, so there is a vacuum. Okay, it's a container which is a vacuum. So it is initially it was a vacuum. To this vacuum container, we are supplying air from a pipe. Okay, this is vacuum or evacuates. Okay, so it is insulated tank which was nothing is there inside. Okay, okay, so insulated tank. Okay, so this is a supply pipe. Okay, so whose pressure? The in this pipe there is a air supplying at a pressure of P. So whose pressure is around 250 kilopascal and temperature is around 400 K. Okay, so from this pipe we are supplying air to this tank. Okay, so he is asking once this tank is completed and it is reached by same pressure. So now it has been reached again same pressure. So what is the temperature inside? What is the temperature inside? Okay, so it is a problem of discharging or charging of tank. Discharging or charging of tank. Okay, so here what is happening? So whatever the energy it is having, same energy it is transferring to this air. Okay, so that is nothing but, so we can use this for charging tank. Okay, that is MP that is enthalpy of this fluid, this air which is flowing here, will be supplied same energy, it will be given to your this air to this tank. So that is your changing internal energy. Okay, whatever the energy it is having, that will be transferred to your air. Okay, so that is, so previously what is the air inside? Nothing is there, so m1 is 0 since the tank is empty. Okay, and so that is why it is mp into hp, that is equal to m2 into u2. Okay, and they have given that this gas is a perfect gas, so it is hp is nothing but cp into t. Okay, cp into tp, and ut is nothing but cp into t2. Yeah, cv, not u is nothing but cv into t, right? Okay, it's not cv, it's cp, it's cv into t2. Okay, so and the mass is same, so mass flow rate is same as this one. Okay, so that is why your mp and m2 are equal. Okay, then this will get cancelled, so then we'll be having cptp is equal to cvt2, then t2 is equal to cp by cv into tp. So that is nothing but, what is cv? cp is nothing but 1.005, it is given, and this is 0.707 into tp is 400, so it is around 559.89 k, 559.89 k. Okay, so this is the answer of air temperature after it is been filled with the air coming from the supply line. Okay, so that is one thing they have asked, and one more question will solve in heat transfer. Okay, so here they have asked this question. Okay, it is a cube with a side a is equal to 30 mm, and this is also 30 mm because it is a cube, and inside which we have a sphere of radius 10 mm. Okay, and this sphere will be treated as first object and cube as treated as second object. Okay, so they are asking what is the view factor of cube, that is f22 itself, that is f22. Okay, they are asking the value of f22. Okay, so here since the sphere is convex, therefore f11 is 0. We know that f11 plus f2 f12 is equal to 1, so f12 is equal to 1 because f11 is 0, and we know that from reciprocity relation a1 f12 is equal to a2 f21. Okay, what is a1? A1 is the surface area of the sphere, that is 4 pi r square. Okay, and f12 is 1, and a2 is the surface area of the cube. Okay, each side is having surface area is a square, so that is 6 sides means 6 a square. Okay, substituting these values into this 4 pi r square into f12 is 1, a2 is 6 a square into f21, which we need to find. Okay, so that is the f21 is equal to 4 pi r square by 60 a square, that is 4 pi into 10 square by 60 into 30 square. So that is F21. So we'll be getting around 0.23. Okay, and we know that F21 plus F22 is equal to 1. So F22 is equal to 1 minus 0.23, that is 0.77. So F2T is nothing but F2T is value of F2T is 0.77. So that is the answer for this question. Okay, let us move on to the next question. So let us do problem in theory of missions. Okay, so that is they have given that one propeller shaft is taking so this is the propeller shaft, but he has given that it is rolling. So they have given that it is a rolling. So in the and they have given what is the angular velocity or mass moment of, first of all, mass moment of inertia of propeller shaft. That is I is equal to 100 kg meter square. Okay, and rotational speed of propeller, that is omega is equal to 12 radian per second. Okay, but it is rolling. They have given it is rolling. Rolling means your precision velocity, precision angular velocity, that is omega p is 0. Okay, it is clear that as omega p is 0, so we can easily say that your gyroscopic couple C is equal to, that is I omega p. So omega p is 0, so your gyroscopic couple is 0. Okay, simply you can say that it is 0. Okay, so that is another question. Let us solve one more question in heat transfer. Okay, they have taken the long fin. Okay, so for long fin, okay, what is the heat transfer from the long fin? That is Q is equal to root of HPKA into Ts minus T infinity, right? This is Ts is nothing but your surface temperature to which your fin is attached. T infinity is your ambient temperature or atmospheric temperature. Okay, H is convective heat transfer coefficient. And P is perimeter of your fin. K is thermal conductivity of fin. A is cross-sectional area of fin. Okay, so and from this we can say that K is directly proportional to root K. K is directly proportional to root K because he has clearly mentioned that keeping other parameter, keeping other parameters as constant. Okay, so key is directly proportional to root k, and they are clearly mentioned that thermal conductivity is increased, doubled. That is k2 is equal to 2k1. So then this will be q dot q2 dot or q dot because it is in kilowatts. Okay, that is why we are taking dot. So that is q dot. Kilowatts or watts means it is per second, joules per second. That is why it is mentioned as dot. Okay, so q2 by q1, q1 q2 dot by q1 dot is equal to, you can write k2 root of k2 by k1, that is equal to root of 2k1 by k1. So that is nothing but root k, root 2. That implies q2 dot by q1 dot is equal to root 2. So that is the question they have asked. So what is q2 dot by q1? That is the question they have asked. Okay, so one more simple question we will solve in uh, fluid mechanics. So there is a submarine. This is a submarine. Okay, so submarine will is under water. Okay, the atmospheric pressure is given as 101 kilopascals. Okay, so and they have given the pressure on the surface of the submarine, that is absolute pressure. Absolute pressure on the surface of submarine, P absolute is given as 4.2 megapascal. That is nothing but 4.2 into 10 power 6 pascals. The submarine is under a depth of h, let us say. Okay, and we know that what is the pressure over here. So over here or here. So this is your P absolute. So P absolute is nothing but P atmosphere plus rho gh, right? So this is the pressure due to height of the water above the submarine. Okay, so this is a small capital H. Okay, so they have given the density of water because it is a salty water. So the density of the water is around 1050 kg per meter cube. Okay, and atmospheric pressure is 101 kilopascal. Just we need to substitute into this, and G is also given as 9.8. Just substitute in to get the height, depth in which up to which the submarine is there. Okay, at what depth the submarine is there. So that is P absolute is 4.2 into 10 power 6 is equal to 101 into 10 power 3 plus, so rho is 1050 into 9.81 into 9.8 into H. Okay, so we'll be getting around the value of H as 398.35 meters. 398.35 meters. Okay, so this is about this. Okay, that the answer for this question is this. Next, we will solve one more question in this one. Strength of materials will solve one more question. So that is the strength of materials question we are going to solve. So they have given a overhanging beam. So which is having a UDL load, which is carrying UDL load of value 20 kilonewton per meter. Okay, and these are given as 2000 mm, so nothing but 2 meters, and this is 1000 mm, that is 1 meter. Okay, so here, so first we need to find out the reactions for this beam. So let us say this is A, B, and this is, let us say, B, C. So what is the reaction at this support? So our first we will draw the free body diagram of this. So this is your RVA and this is your RVB. So this is your UDL. So this is 20 kilonewton per meter. Okay, so this is 2 meters and this is 1 meter. Okay, so let us take the moments about A and equate it to 0. Okay, so that is so if you convert this UDL into point load, this is 20 into 3, that is 60 kilonewtons, which is placed at a distance of 1.5 meters. Okay, so this is anti-clockwise, that is RVB into 2. Let us take anti-clockwise as positive, and this is 60 into 1.5 is equal to 0. So this is RVB will be around 45 kilonewtons, and we know that RVA plus RVB is equal to 60. So RVA is equal to 60 minus 45, that is 15 kilonewtons. Okay, so RVA is 15 kilonewtons, RVB is 45 kilonewtons. Okay, so now, so once we know the reactions, we can find the shear force diagram. So how the shear force diagram will be looking like? This is A, this is B, and this is C. So what is SF at C? I mean just left side if you see. So or means SF at C is 0 anyway, and SF at B, that is just right side. So that is your 20 into 1, that is 20 kilonewtons. Okay, so what is the sign convention? Run. So it is downward, it is positive. So this is plus 20 kilonewtons. So this is the value, sorry, upwards. So plus means upward. This is plus 20 kilonewtons. And how will you join? It is an inclined line. Okay, similarly at SF at B, just left side. So that is 20 minus 45. So that is minus 25 kilonewtons. Okay, so 20 into 1, this is 20. Okay, and it is minus 45. 20 minus 45 is minus 25 kilonewtons. Okay, that is minus 25 over here. Kilonewtons. Okay, and similarly SF at A. Yeah, just right side if you take. So then this will be 20 into 3, that is 60, plus 60 minus 45. So that is plus 15 kilonewtons. Okay, that is your plus 15 over here. Okay, join these two. Okay, with an inclined line. Join these two with an inclined line. Okay, so we'll be getting some zero value somewhere here. Okay, so let us find out the where the shear force is getting zero. Okay, so let us find out this by using similar triangle method. Let us say it is x, and this will be 2 minus x. Okay, so if I use similar triangle method, that is 15 by x is equal to 25 by 2 minus x. So that is 30 minus 15x is equal to 25x, and this is 40x is equal to 30. That implies x is equal to 3 by 4, that is 0.75 meters. So that is this one, that is 0.75 meters. Okay, so there shear force is getting zero, and here also shear force is getting zero, means it is changing sign from positive to negative. So means that the bending moment will be maximum either, let us say this point is D, this point is B. So bending moment, since shear force is zero, since shear force is zero at D and B, so bending moment will be maximum bending moment will be maximum at B and D. Okay, first we will calculate bending moment at B. So what is the bending moment at B? That is a 20 into 1 into 0.5. So 20 into 1 into 0.5. So that is 10 kilonewton meters. Okay, and similarly bending moment at D. What is the bending moment at D? This is 20 into, so what is the value over here? This is 0.75, and this is 2 minus x, means it is 1.25. Okay, so the totally it is 20 into 2.25. Okay, so that is so this is actually a minus. Okay, and similarly this is minus 20 into 2.25 into 2.25 by 2, and plus, and this is reaction is around 45. So this is 45 into the distance is again 1.25. 1.25. So this is around, we'll be getting the bending moment value as, so this is minus 50.625 plus 45 into 1.25. So this is 56.25. Okay, so this is around 56.25 minus 50.625. So it is around 5.625 kilonewton meter. So the maximum is 10. So maximum bending moment is equal to Bm max is equal to 10 kilonewton meter. That is nothing but 10 into 10 power 3 into 10 power 3. It is in Newton mm. Okay, then the cross sectional area of the beam is given as, so this is 24 and this is 100. So if you apply, this is your M max, M by I is equal to sigma B by Y. That implies sigma B max. We want sigma B max, that is nothing but M max into Y max by I. So this is your Y max. Y max is 100 by 2, that is 50. Okay, so sigma B max is equal to M max is how much? 10 into 10 power 3 into 10 power 3 into Y max is 50 by, it is 24 into 10 100 cubed by 12. So this is the value we'll be getting. So the value of this one will be around it is around 250 megapascal. So 250 megapascal is the answer. Okay. Next, we will do one more problem in machine design. So there is one question they have asked in machine design like this. Okay, in a spring wire, they have given the stress variation like this. Okay, so they have shown the shear stress across the spring wire. And this is the spring wire. Okay, we know that in helical compression spring or helical extension spring, come on, the spring is subjected to direct shear stress and torsional shear stress. Okay, how the direct shear stress will vary across the section like this. Okay, so this is your, let us say this is tau 1 and this is direct shear stress variation. And the torsional shear stress, it is also subjected to torsional shear stress. Okay, let us say this value is tau 2. Okay, this is torsional shear stress. If you combine these two, so your shear stress variation will be like this. So that is, here we will be getting at the inner fibers, it is tau 1 plus tau 2, whereas here it is tau 1 minus tau 2. Okay, this is combining of both direct shear and torsional shear stress. Hence, the answer is whatever the diagram they have shown is a combination of both direct and torsional shear stress. There is one more diagram that is showing a curved shape. That curved shape is for with the stress concentration factor. It is very similar. One more diagram, sorry, a similar diagram we will get. So this is for combining of torsional, direct and stress concentration effect. This is like a curved one. Combining of torsional, direct and stress concentration due to curvature. Due to curvature. Okay. So that is the so that is where this is the answer, combining of direct shear and torsional shear stress. Okay. So we'll solve one more question in this. Okay, so just wait. Okay, anyway, I think we better stop here. Okay, so we'll continue tomorrow. So we'll stop here.